Projectile motion formulae. To solve projectile problems, stick to the formulae and methods you've seen in the previous videos. An alternative method to solve problems is to use these formulae. They are called the projectile formulae, and you need to know how to derive all of these, which you can do using all of the previous methods that you've seen so far with the SUVAT formulae. Because they're difficult to memorize, it's better to stick to previous methods that you've already learned. But you still need to know how to use these and how to derive any of these, which is what we're going to look at here. So the first two have something to do with time. The time of flight is the time taken from here along the path to here, and if you halve that time, you'll get the time taken to reach the maximum height here. And you can derive these using a combination of methods seen in the previous videos, including SUVAT formulae. Now the range is this distance horizontally given by this formula, and the equation of the n-shaped curve given in terms of x and y is here, the equation of the trajectory. Working out the formula for the time of flight, t is in uppercase. So method 1 involves looking at the vertical velocity vectors at the beginning and just when the ball hits the ground at the end. So here we have u sine alpha, that's the magnitude, and it's the same here, u sine alpha, but the arrows point in opposite directions. So looking at vertical motion, taking the upwards direction as positive, so this one is positive and this one pointing down is negative. Using SUVAT formulae, we're not interested in the displacement, so that's the formula without s. V equals u plus at. Substituting these values in gives us this. Rearrange to make t the subject. So this is the first formula. The time of flight, the time taken for the ball here to follow this path and hit the ground at this point. Now here's the same attempt at working out the time of flight formula again, but this time we're going to look at the displacement in the y direction, the vertical displacement, here and here, and they are both equal to 0. So again, the upwards direction is positive, so sy is 0. The initial vertical velocity, u sine alpha, and it's positive. We're not interested in the velocity here vertically, so I've crossed that one out, and then using an appropriate SUVAT formula, and we don't want v, so s equals ut plus half at squared. Substituting our values in, we have a quadratic formula in terms of t. We've got a term with t, this one has t squared. We can factorize out the t, and then either this part is 0 or everything in the brackets here is equal to 0. And rearranging this to make t the subject, we have the same formula as before, but there's more working out here. We discard this one because we know that the vertical displacement will be 0 at the beginning, initially when t equals 0. That's not the one we're after. This is the one that we need for the time of flight. Now if we take the time of flight and we halve that time, it will give the time taken to reach the maximum height. So we get a new formula. So this is the time of flight, and if we halve it, so all I'm doing is dividing by 2, so t divided by 2 here, and the right hand side, if you divide by 2, the 2 will cancel. So this is the time taken to reach maximum height. It's the time of flight divided by 2.